on that third image of the liver, when you're doing the portal vein and the liver gets really big down there, that's why I tell you to adjust your TGCs, because sound is going to be weaker by the time it gets to be 17, 18 centimeters deep. Okay? That's why I tell you to adjust your TGCs. Okay? So the output power is not going to make the whole image uniform from top to bottom. Okay? It's going to make the whole image brighter as a whole. Brighter or darker as a whole. So, guys, we know this right here, right? We know what that is. We don't like that. Well, nowadays you don't have to worry about that unless you got what's that called? Dish. Unless you got dish, and it's raining like today, you're gonna be home today and you ain't gonna be able to watch TV.
Antenna.
But back in the days, this was a bad sign. This is what we would consider noise, meaning that we have unwanted information on our TV. Now we can't see what we want to see. We may can hear it, right? We may be able to hear. I can hear, Sanford and Son going on in the background, but I can't see it.
We got the TV at the top, show pictures.
Okay, that too. That old school with. Okay, but this is considered noise, right? Noise is that random persistent disturbance that obscures or reduces our signal's clarity. Okay, remember, noise doesn't have to be the whole screen looking like this, right? Noise we can actually see the picture sometimes a little bit in between this noise, right? But we can't see our picture clearly. So that's what noise is. That persistent disturbance that obscures or reduces our signal's clarity. We're not able to see what we need to see clearly. Okay? And in sagittal, right? And you're doing it. And you're looking at, say you're looking at the mid to distal aorta, you're right there, you're right above the umbilicus. When you're looking at the mid aorta, because it's a lot deeper, it may have a lot of noise associated. Remember, you can't always get it super clean. Remember, it's a blood vessel. It should be black, right? Mm-hmm. It has fluid in it. It should be black. It shouldn't have anything in it. But sometimes you can't get it to be cleared up, right? It'll have those kind of, hazy looking lines in it, right? That's what we're talking about. We're talking about noise. Okay? Those low level echoes that give us undesirable, unwanted information. All right. Okay. So, when we're talking about noise, we have what's called the signal to noise ratio, the S to N ratio. That is a comparison of meaningful information to contamination. Okay? So our signal will be our meaningful information. Our noise would be our unwanted, okay? Our meaningless information. Okay? That's the comparison. That's what the signal to noise ratio is. Ooh. Since you're standing, can you cut on the machine for me? Let's cut on IU22. In the lab.
Oh, lab?
Yeah, since you're standing there. Sorry. You won't miss much. Okay. So again, the signal to noise ratio is just a comparison of meaningful to meaningless information. Okay? Meaningful information is our signal. That's what we want to see. Okay? Meaningless information is our noise. That's our contamination. That's what we don't want to see. It's blocking, it's obscuring our visualization of meaningful information. All right. So, and you can see clearly by our images here. I would say in ultrasound or in X-ray as well, it would be like a contrast deal, right? If we have what's called high contrast, meaning we have really like harmonics, that would increase our contrast, right? Going to make our blacks blacker and our whites whiter. We have a real black and white image, correct? That would be a high signal to noise ratio right there. High signal to noise ratio. Signal is much stronger than the noise, creating a higher quality image. That's why you guys like harmonics so much. When it's useful. Okay? That would be a high signal to noise ratio. When we have a much higher signal than we have compared to our noise, we always want that, right? We would prefer not to have any noise. Okay? And a low signal to noise ratio is when our signal and our noise are basically at closer levels. So a high signal to noise ratio would be like this. A low signal to noise ratio would be like this. They're very close together. Our signal comparison to our noise. Okay? In that case, we're going to have a lower image quality and more visible contamination, which is going to make our image less diagnostic. Okay? My images, again, I formatted these images. Your images in the book are a lot better, or you can actually see some of that contamination, that grade going on within the blood vessel right here. Okay?
So
You see?
any bioeffects with the high.
No, not concerning bioeffects. Not concerning bioeffects. Noise is just, those, because noise is like, when you say if a signal comes back very, very, very weak, that's what's going to contribute to the noise. If we have a really, really low signal, it's not giving us good information, but I can't turn my gain down or turn my output power down low enough to get rid of it. Right? It's still going to be there. Okay? So again, high signal to noise ratio, meaning that our signal to noise are very far apart. We have a much higher signal than we have noise. Okay? A low signal to noise ratio, meaning that our signal and our noise are about on the same level. Okay? You're going to have higher contrast with a higher signal to noise ratio, meaning you're going to have a more black and white image. Okay? When you have a lower signal to noise ratio, you're going to have a more gray image. You're going to be able to see those range of grays. Okay? And you can see it right here. All right? Any questions on signal to noise ratio? Any questions on the pulsar so far? The pulsar. What creates our amplitude? Okay, because that's all we talked about so far is the strength of our sound. We haven't gotten into PRP and PRF yet. Okay, no questions. Yes,
Which
ma'am.
one is most desirable on a signal-to-noise ratio?
The higher signal to noise ratio is more desired because we do want more signal than we want noise. Unfortunately, say for instance, when we're looking at the liver, because I'm comparing it to contrast, I really want to be able to see the gray shades in my liver, right? But I still don't want a whole bunch of noise obscuring. Say for instance, when you're looking at bowels create a whole bunch of noise. That peristalsis, that air in the bowels, is going to create a whole bunch of noise on the image, which is going to make it less visible for us to see what we need to see beyond those bowels. Okay, so a high signal to noise ratio is more desirable. Okay. So, how does transducer output affect noise? If the transducer output is low, noise is more likely to degrade the image. So if we have our transducer output on the lower voltage, we're going to be effectively, we're going to have more noise. Why? Because we're sending out weak signals, right? And we're going to get back weak reflected signals. Okay? Remember, noise is consisted of low level echoes coming back to the transducer. Okay? Therefore, increasing the output power also increases the signal to noise ratio, and that's also the most common way to improve the S to N ratio, our signal to noise ratio. Okay? We always want more signal than we want noise, all the time. All the time. The way we improve that is by increasing our output power, increasing our acoustic power, increasing our pulsar power, and all the other synonyms associated with transducer output. So, those are all of the things that affect the amplitude, correct? Our signal to noise ratio. We talk about our pulsar. Those are what's affecting the actual amplitude of our beam. Okay. Still dealing with the pulsar, because we know the pulsar also determines PRP and PRF. PRP, we know PRP to be what, Farnaz? What is the PRP? Absolutely, I heard that. The time that it takes from the start of one pulse to the start of the next pulse. Okay, one on time, one off time. That's our PRP. Okay, what's PRF? Ubu?
Is the frequency on how many pulses we get,
Number.
on how many,
Second.
is it how many numbers of pulses we get?
Per second.
Per second.
How many pulses are sent into the body each second? Okay, that's our pulse repetition frequency. What's that relationship, Dewey?
It was
They are inverse. What else?
reciprocals.
They're also reciprocals, correct? They're also reciprocals. Okay? So whenever we determine pulse repetition period, we're also going to know our pulse repetition frequency. All right? So In addition to controlling the strength, we already talked about how the pulsar controls the strength of the sound. When the signal vibrates more forcefully, we're going to get a stronger signal. When it vibrates the PZT gently, we're going to get a much lower signal. Okay, that's how it's going to affect the strength of our sound beam. Okay, but the pulse repetition period.
So,
Go ahead.
okay, if you say that you can have strong or low, depends on the voltage.
Mhm.
Okay.
Absolutely.
So if we have 0 to 100,
Mhm.
depends on between, like if I have 50, I'm gonna get
Kind of that mid-range.
yeah.
If you have it up to 100, your image is going to be very, very bright. If you have it down close to 1, your image is going to be very, very dark. Okay. The pulsar also determines the time between one voltage spike to the next. Right? What's that determined by, guys? What's our PRP determined by? What determines the PRP?
The depth.
The depth, right? Because remember, we don't change our pulse duration. We only change the listening time.
Right.
Okay? And only thing that changes between that is how far the sound has to travel. The depth. Okay? The length of the pulse is going to be the same regardless. Our pulse is going to be the same regardless. Only thing we're changing is how far that sound has to travel. Okay? That's the only thing we're changing right there. All right? So, of course, that's going to affect our pulse repetition frequency. If we're traveling at a more superficial distance, we're going to be able to send more pulses per second now, right? Because now our pulses are already reflecting back sooner. They're able to come back to the transducer sooner. Remember how ultrasound works? We want to send the pulse out. We're going to wait on that sound to come back before we send out another one. Okay? That's the theory of ultrasound. That's how it's supposed to work. Okay? So the PRF will be determined as well. The effects it has on the image, of course, PRP and PRF are determined by how deep the sound travels. Okay? PRP determines the maximum imaging depth or the depth of view. Okay? So on some systems, when you're actually changing your depth, they won't give you the depth and the number. They will actually have PRF on there. It'll actually have PRF on there. So you'll know if I'm making my image more shallow, if I'm decreasing my depth, then I'm increasing my pulse repetition frequency. Okay? So some machines, you actually see where it's changing the PRF. Okay? So again, we know that's an adjustable feature, right? Because we change the depth all the time. All right? So we have much deeper imaging. Now we have a much longer PRP, and now we have a higher PRP. We have a much lower pulse repetition frequency, right? Because it's going to take this a lot longer to come back before we send out the next pulse. Okay. When we have shallow imaging, now we have more pulses per second, which is our PRF. Okay. But now we can see that our pulse repetition period, the time from here to the next one, the next pulse is a lot shorter compared from the beginning of this pulse to the beginning of this pulse. Okay. So the maximum imaging depth is also determined by the pulsar. Okay. And that's just the chart in the book right there. What time is it, guys?
11:30.
That's its time? I have 20 minutes? Okay. So, next thing up, guys, we have the beam former. What did I say the beam former does?
Forming the beam.
Form the beam, right? It forms the beam. It's going to steer and focus our beam, right? It's going to communicate with each PZT element and tell it how to react, okay? It's going to send those electrical signals created from the pulsar. So the electrical signal is going to go from the pulsar to the beamformer. The beamformer is going to distribute the total strength of that sound into each PZT element. You guys got me?
So the beam is the sound.
The beam is what's coming out of the transducer. But that is sound waves, definitely. Acoustic energy. Okay? So the beamformer is the part of the transducer that functions during transmission and reception. Okay? With phased array transducers, multi-element, multi-focus transducers. Okay? The beamformer it functions during both. Okay? Because why does it function during both? Do you guys remember? Because we have something called dynamic receive focusing, right? That focuses the beam during reception. So that's why the beamformer also functions during both transmission and reception. Right? During transmission, it receives the pulse's electrical signal spike and distributes them to the PZT. Okay? So one single electrical signal is going to come from the pulsar. The beamformer is going to be the distributing factor of how each single PZT element gets its signal, gets its electrical signal. Okay? It coordinates the complex electrical signals sent out to each active element. Meaning that, remember, it coordinates like if we have, can you turn that like that? 1 second. So if we have our, this is our pulsar. Our pulsar is going to send out. That's my electrical signal right there, guys. I'm right ES right there. That's my electrical signal. It's going to send out my electrical signal. Okay. This is my beamformer right here. Beamformer. Okay, so that's my beamformer. These are my elements right here, guys. These are my elements down here. The little balls are my elements. Okay, so it's going to take this electrical signal, that big electrical signal, and the beamformer is going to divide that electrical signal amongst every PZT element. Okay, so we know that how it divides it is going to depend on the shape of that beam, right? So if it divides this right here, boom, boom. So it's taking all this strength should equal the beam strength. Okay, whatever the pulsar produces is going to equal however the beamformer is going to distribute all of those signals to the actual PZT elements. So I drew this right here. These are my electrical signals right here. These are my ES created from the beamformer. Okay, so I drew this on an actual slope. So the time it sends those signals out is actually going to focus this beam because I have it in the slope, right? Because I have it in the slope. So it's going to cause those signals to be focused now. Okay? So the beamformer is actually sending out those complex electrical signals to each active element. This right here, the beamformer, the system electronics, the actual wire itself connected to the element, that's called a channel. Okay? So that's called a channel right there. Okay? So that's what the beamformer does. It's going to take the electrical signal from the pulsar, and then it's going to distribute them to the active elements in those complex ways we talked about. We talked about how it sends. Remember we talked about how we have side lobes and grating lobes, right? And how we like to send the stronger signals to the outside, right? So we have less grating lobes, correct? With phased array transducers. So to send those stronger signals to the outside, weaker signals to the middle. Okay. The beamformer also controls that. Okay. So the beamformer is doing what it says it does. It's forming our beam. Okay. It has the ability to steer, focus our beam. Okay. Yes, ma'am.
The voltage or energy comes from up to down, but this arrows comes to up or down.
We're traveling down. These are just the electrical signals. I just drew them in triangles. The shape.
They look the same. It shows they are going up.
They're not, that is not showing direction. They're traveling to the active elements.
Okay.
They're traveling down to the active element. I guess I should have drawn upside down triangles. I'll do that next time. I'll do that next time. Guys, I think I said, I have 10 minutes left? 5 minutes? All right, real quick, guys, because I have the machine on, I want to show you guys something in the lab real quick before I let you go. Roll.
Let's go, guys. Yeah.
Thank you, man. So, guys, real quick, on the IU-22, well, on this machine, that far button over, you see that top button right there, point to it? That says what? Acoustic power. That says acoustic power. That's how we're gonna change the strength of our signal. On this machine right here, it's called output power. Okay? So what we do to find it on the IU-22, I hope I'm not blocking anybody, Mario, you can see? Sit down. Thank you. So, on IU-22 itself, we're just gonna go to the next screen. Next screen, you're gonna see right here, output power, right there. That's how we're changing the actual overall brightness of the image. Okay. So I'm gonna scan myself real quick.
You gonna do that now?
What? I'm gonna show you how it works. Lot in. So scan my thyroid. Right there. And can you turn my acoustic power up clockwise for me? Turn it up.
To the right?
So, okay, so it's already up at the highest, guys. It's already up at the highest. So I'm gonna turn the acoustic power down. Look how it changes the overall brightness of the whole image to now it's dark, right? When I turn it up, now you can see
Wider.
you can see it is
at 100%.
now it's at 100%. It's at 100%. But doesn't that look just like this?
Yes.
Looks just like this. The only difference is, well, it's two differences. Output power functions during transmission. The is actually changing the strength of the sound coming to me. Okay? When I change the gain, the 2D right here, that's actually changing the strength of the signal just on the monitor itself
So-
during reception.
So the output power has something to do with patient exposure.
Absolutely, absolutely. So that's why I said if I have this really bright image right there, the first thing I'm going to do should not be to turn my gain down. First thing I should do is to turn my acoustic power down, because now I'm helping the patient as well by decreasing that patient exposure.
But I have a question.
Yes,
You
ma'am.
can increase the gain to get that right. That,
I just made it just so you can see the effect. I'm doing dramatic effect
Okay,
right now.
gotcha.
Dramatic effect.
So
Dramatic
you're just
effect.
not sending too much electricity.
I'm not
to
yeah,
the
I'm not
patient
sending too
organ.
much
Okay.
sound to the patient.
Sound or voltage?
Voltage to the machine, sound to the patient.
Mm-hmm.
Yeah, because remember we're not sending any electrical energy to the patient, because once it hits the PZT, it's creating sound waves. The strength of that sound is determined by the strength of that voltage. So they're directly related. If I have a high amount of voltage, I'm going to have a higher signal strength sound beam coming to the patient. Okay, but I just wanted to show you guys that real quick to show you that output power again. It's on the previous screen. So hit next from the first screen, and now I can change my output power. I turn it down. See how it affects the overall brightness of the whole image? Same thing with the 2D. Same thing with the gain. It's going to affect the brightness of the entire image. Remember, it cannot change make it uniform from top to bottom, right? Because as I get deeper, now it's just dark on the bottom. It's not going to make this whole image uniform, right? It can only change the overall image. So the whole image is going to be dark, or the whole image is going to be bright. okay? Because of attenuation.
When do you use
This is the same?
When do you use that?
What output power? If my image is too bright, I want to decrease my output power to decrease the patient dose to the patient. Okay. If my image is really dark, then I don't want to turn up my output power. I want to turn up my gain because that's a receiver function. It doesn't affect patient dose. That's the number one thing about transducer output is that it affects the patient dose. Okay.
So, but we rarely mess with that.
In real life, you guys probably didn't even know it was there until I showed you some months ago when you first
Well,
started.
no, I just remember the beginning of
The school,
year.
right. But as far as the functional button, you guys don't really use it, right? But I'm telling you, if you want to use, that's how you use it. Okay.
What about TGC?
TGC, that's the button, or those are the knobs, and that's a receiver function as well. That affects the brightness at different depths. Okay. But right now, I just want to stick to the pulsar because that's the transducer output. Because that's what we're on. When we get to the receiver, we're going to talk about the TGC. We're going to talk about the gain. We're going to talk about compensation, and compression. We're going to talk about compression, how that works from a really gray image to a really high contrast image. All of these things are changing the reflected signals. Okay. When we talk about transducer output, that's changing the transmitted signals, the signals coming to the patient. Okay.
So we don't use, right? We don't use this. Just when we learn in the class.
Right, but when you answer on the test, and I ask you, say this image is really bright overall, what should I do first? Your answer will be turn down or decrease my acoustic power, decrease my output power, decrease my transducer output. Okay? So I just wanted to show you guys where that button is. Again, you hit next from the home screen. It's transducer output power is right there. On that machine over there, it's right on the top left. Transducer, what it say? Acoustic power? Acoustic power. Okay?
But it's not gonna work without pressing next. Like just use this by itself. Like.
Nah, cause it's a dual function button. It didn't have a function on the first screen.
Okay, yeah.
It doesn't have a function on the first screen. So that's all I wanted, guys.